Dear students, today's topic is capacitor and capacitance. What is a capacitor? A capacitor is a device which is used to store electrical energy or by storing electric charge. That is called a capacitor. Normally, a capacitor is a system of two conductors 1 and 2 having some charges, suppose Q1 and Q2, and potentials V1 and V2. And now the potential difference between the two conductors V1 minus V2, and the charge difference is Q1 minus Q2. Normally in practice, you will take one of the conductor have charge plus Q, other conductor having charge minus Q. Normally, you will take this type of charge configuration. Or one conductor may be taken having some charge Q, and other conductor may be assumed to be at infinity. And basically, the capacitor's function is to store electrical energy by storing electric charge. At any instant, the potential difference between the two conductors depends upon the charge, because potential difference, you know, it is the work done to transfer a charge from unit charge from one point to other. Now the potential difference, suppose V is equal to V1 minus V2. This is the work done to transfer a unit charge from one point to the other. And if Q is the charge of the capacitor, then the potential difference between the two conductors at any instant depends upon the charge. And here Q is called the charge of the capacitor. Although the net charge of the capacitor is 0. Here Q is represents charge of one of the plates or one of the conductors of the system. Now at any instant, Q is proportional to V, or we can write Q is equal to CV, where C is the proportionally constant called capacitance of the capacitor, or C is equal to Q by V. So capacitance equal to charge by potential difference or charge by potential. And if V is equal to 1, then C is equal to Q. That means you may define capacitance of a capacitor as the charge required to increase the potential difference between the two conductors by a unit amount. That means if more charge is required to increase the potential difference by a small amount, capacitance will be large. That means more charge can be stored. That means more energy can be stored. So C is equal to Q by V. If V is very small, C is large. That means large amount of energy or charge can be stored. Now we can define the capacitance of a capacitor as the charge required to increase the potential difference between the two conductors by unit amount. Then what is the SI unit of capacitance? The SI unit of capacitance is farad. So 1 farad is equal to, it is represented by symbol F, that is equal to 1 coulomb by 1 volt. So you may define 1 farad as a capacitance of a capacitor if 1 coulomb of charge can be transferred from one conductor to another by providing a potential difference of 1 volt. So this way we can define 1 farad. Then what about the dimensional formula of capacitance? Capacitance is equal to Q by V, and you know charge is A into T, because you know I is equal to Q by T, charge by time. So charge is current into time. For current we are writing A, for time T, so charge is AT. What about the potential difference? you know potential difference V is equal to wire done by charge, and wire done is M L2 T minus 2 divided by Q is AT, so that what will get M1 L2 T minus 3 A minus 1. Just put the value of V there. So now AT divided by M1 L2 T minus 3 A minus 1. So that is equal to M minus 1 L minus 2 T 4 A 2. So this is the dimensional formula for the capacitance. Then the capacitor can be represented by a symbol like this. This is the symbol for a fixed capacitor, and this is the symbol for a variable capacitor. It is similar to a resistor, like a capacitor. Here this is fixed capacitor, this is variable, means you can change the capacitance. Now what is the principle of a capacitor? Under what principle a capacitor works? So let us take two conductors 1 and 2. Suppose it carries some charge, positive charge plus Q maybe. Now this conductor carries charge plus a positive charge. Now another conductor 2 which is uncharged, it is placed near this. When the uncharged conductor is placed near it, due to induction, negative charges are induced in this side, that means nearest to conductor 1, and the positive charges are induced in the other side, that means farthest end of the second conductor. Now, what is the tendency of, V is proportional to Q, that I have shown. So now, this negative charge has the tendency to reduce the potential or potential difference, and positive charge has a tendency to increase the potential difference. So now in the next step what I do, suppose this end of the conductor is connected to earth. When this end is connected to earth, what will happen? These positive charges will be neutralized due to the flow of electrons from earth to this. Earth is always considered as to be at zero potential. So now you see these charges are neutralized, and these charges will remain there. These negative charges, they are called bound charges. This is due to the attractive force of these positive charges. This will remain there, and this will reduce the total charge. That means this will reduce the potential difference between the two conductors. That means they will increase the capacitance. C is equal to Q by V. If V is reduced, C will increase. So this way, capacitance of the capacitor will be increased. Then what is the principle? The principle of the capacitor is that when an earth conductor is placed near a charged conductor, then the capacitance of the system increases considerably. Once again, the capacitance of a conductor increases considerably when an earth conductor or earth connected conductor is placed near it. This is the principle of a capacitor. Now let us find the capacitance of an isolated spherical conductor. Now consider a sphere of radius r carrying a charge plus Q. Then you know the formula for capacitance. C is equal to Q by V, charge divided by potential. Then what is the potential due to a spherical conductor? So the V will be equal to, that will be similar to a point charge, 1 by 4 pi epsilon naught Q by R. This is the potential due to a spherical conductor. That means V is equal to 1 by 4 pi epsilon naught Q by R. So capacitance C will be equal to Q divided by V. So 4 pi epsilon naught Q by R. And so C will be equal to now 4 pi epsilon naught R. And it is very clear from the expression that C is proportional to R. Capacitance of the spherical conductor is proportional to its radius. It does not depend upon the potential or the charge. It only depends upon the geometry of the conductor. Now, as it is a spherical conductor, it depends only on the radius or size of the conductor. So, more is the radius, more is the capacitance. It can store more and more charge, that is more electrical energy. So, later on, again you will see that capacitance depends only on the geometry of the conductor or geometry of the system of the conductors. Now, take an example. Let us calculate the capacitance of earth. And earth can be considered as a sphere of radius r. You know the radius of earth. R is equal to 6.4 into 10 to the power 6 meter. Then what is the capacitance? C will be equal to 4 pi epsilon naught. You know the value of 4 pi epsilon naught is 1 by 9 into 10 to the power 9 into radius is 6.4 into 10 to the power 6. That means if you calculate, you will get the value 711 microfarad. That means 10 to the power minus 6. Micro means 10 to the power minus 6 farad. And now farad is a very large unit of capacitance. If you are taking earth as a sphere and calculating the capacitance, the value is coming only 711 microfarad, 10 to the power minus 6. So that's why the farad is a very large unit of capacitance. So practically, the units of capacitance used are microfarad, nanofarad, picofarad, etc. Microfarad 10 to the power minus 6 farad, 1 nanofarad 10 to the power minus 9 farad, picofarad 10 to the power minus 12 farad. So these are the units of capacitance. Now this is we have found the capacitance of a spherical conductor. So afterwards we will find the capacitance due to different type of charge configuration.